Previously, we have seen the hardware design of this RISC-V microcontroller dev board, sent it for manufacturing and wrote some firmware test examples. In this video, we will create an even more optimized minimalistic version of this board around the same RISC-V microcontroller. It's a tiny footprint board that can easily replace any DIP package microcontroller and fit into a breadboard. Personally, I always use boards like this for prototyping projects or crazy ideas. I just never touch my stack of MCUs that are becoming much more expensive, low on stock, some of which are now in RFNDs. Mostly none of these gonna end up on a design of mine, with some exceptions of microchip parts that are still relevant to this day. To be honest, I'd like to keep those relics to show to my kids someday. Anyway, this video is sponsored by JLCPCB, the go-to fab house for many of our projects. More on them later in this video. Let's start off with an overview of the schematic design of our board. This is the schematic design of our dev board. As you can see, it's much more optimized than the previous board. It has an LDO for the input power regulation, some indicator LEDs, the I/O port headers, and the MCU circuit itself. The DC input voltage is regulated down to 3.3 volts. However, this microcontroller can also operate at 5 volts VDD, as mentioned in one of the comments on the previous video. And he also mentioned that we can use the internal oscillator and neglect this external oscillator. The difference between using the internal oscillator and the external is that the external oscillators are much more accurate and stable over the various temperatures and operating conditions. If your applications are not strict on timing requirements and can tolerate some variance in the oscillator, you can use the internal oscillator and omit all of these parts. And you can also remove this LDO but keep one or two of those bulk bypassing capacitors. If you would like to operate at 5 volts, for me I would like to operate at 3.3, so I will keep it as it is. But I just wanted to let you know that this microcontroller is mentioned in its datasheet that it can operate at 5 volts. All those pins are 5 volt tolerant. Even the ADC will adjust itself and will work at 5 volts. So you need to keep this in mind. Given that information, there is not much things that we can mention in the schematic. All of the microcontroller's I/O pins are exposed to those pin headers. And that's all. We have explained this oscillator thing in the previous project. And we have also tested the WCH link programmer and debugger for this microcontroller. So all you need to do to debug or flash your code to this dev board is to connect this SWIO pin and the ground and VCC to the debugger, and it will work. It has also a UART to USB CDC converter on the same debugger device, and we will test this UART functionality in today's project. Let's now have a look on the project in KiCAD. This is our schematic. And this is my PCB layout. It's very simple board and it's very tiny. The spacing between those two rows of I/O pins are made in such a way that it takes only 2 rows of each half of the breadboard. So it takes very tiny space on your breadboard. And this is the 3D view of our board. All of the connections are point-to-point connections. There is no thing that you need to pay much attention to in this design. The onboard LED can be removed if you want to use this PC3 pin. If you want to use it for your own applications, you don't need the LED. You can just remove this R4 resistor from the board. By unsoldering this resistor, you are free to use the C3 pin as you want. And I believe that's everything about it. Now we will place our PCB assembly order at JLCPCB. This is the plugin I use for generating the fabrication files from KiCAD. You have to click on this button and it will generate all the fabrication files needed by JLCPCB. We will head over to JLCPCB, add our Gerber file. Here is my Gerber file, and the system has picked up my design. As you can see, I will change the board color and I will leave every option as it is. I will enable the assembly. I will assemble 5 of these boards, and it's a only top side assembly, and I will click next. Here is another view for my board. I will click next. Here we need to upload the BOM file and the component positions for the PCB assembly. Here is my BOM file, and here is the positions file, and we will proceed. It has picked up all of the components in our board, and as you can see, all of these parts are basic parts and only 2 are extended parts. As I have mentioned in the previous project, that every extended part in your BOM file will cost you 3 USDs in order to load the pick and place machines with these non-standard parts. This microcontroller is actually in my stock, that's why it's costing me nothing, because I have previously bought some of these parts in my library at JLCPCB. The stock of these microcontrollers is fluctuating, that's why I bought some of these to secure my future projects. Everything else seems okay except for this crystal oscillator. Our board has only one crystal oscillator. We are going to assemble 5 boards, so we should see here 5. Maybe there is shortage on the stock. I will copy this part number, search here for the parts. It looks like there is no shortage on this crystal oscillator, and the minimum purchase quantity is 1, not 9. I don't know why it has picked up in this way. I will re-upload the BOM file. Maybe it's a bug in the system. It hasn't corrected itself. Search it here and click this select. It didn't also work. Maybe select another one. And it has now picked up the correct number of the oscillators. Let's do the search again. Use our original part, select, and it's 9. It's insisting on this thing. I don't know why it's behaving like this. We will proceed. This is how it has picked up the positions of our parts. I will right click on the board, drag it into the middle and zoom in. Here we need to check the positioning of the ICs and the diodes for the LEDs. We will cross-reference the KiCAD design. Yeah, this is the pin number 1 of the microcontroller, and the LEDs are positive on the right side. We will have a look again, the positive on the right side, and the microcontroller is placed correctly, so we will proceed. As you can see, the cost of the components, all of which are 1.2 USD. However, we are paying extended components fee of 6 USDs because we are using 2 extended components. We will select research DIY, save it to the cart, pay for the order, and wait for the delivery. After receiving the boards, we will solder a couple of pin headers, one on each side of the board, slap it onto a breadboard, and get to the test. First of all, we will create a LED blinking example to test the onboard LED. We will head over to the MounRiver Studio, click on File, New, MounRiver Project. Here we will enter the part number for our microcontroller. It's this F4P6. You can rename the project however you want. Select the non-OS project template and hit Finish. After that, head over to the project here from the navigator under User, main.c, and copy and paste this code into your main.c file. It initializes the LED pin, which is pin number C3, and it sets it high and low with this delay. After that, we will click on the compile button or build all, and we will connect our board to the debugger and hit the download button. Let me connect the debugger to my board, and it has now been connected to the PC. Let's hit on the download button. Now we have got our onboard LED to blink, as you can see in this demo. Now we will move to the next example, which is PWM example. I should have mentioned this, but the pin that I have chosen for the onboard LED is also a PWM capable pin. As you can see here, the pin C3 is the timer 1 channel 3 pin. Using timer 1 channel 3 as a PWM output will enable us to control the brightness of the onboard LED. Here in this PWM example code, there is a initialization function that initializes the timer 1 channel 3 in the PWM mode, and it also initializes the pin C3 in the alternative function mode. I have explained this PWM and the GPIO code in the previous video, so we will just take the code as is from here into our MounRiver Studio project, compile it and flash it to the microcontroller, which as you can see is now dimming the LED on and off. Next up is the UART test example. In this example test, we will operate the UART1 peripheral in TX mode at this baud rate. We will connect the UART1 in software to the printf function. So the printf function will send UART messages on the UART1 peripheral. And this is done for us in the debug.h file, which we need to include to have this printf feature. And we will send the debug messages to the PC over the USB UART bridge inside of the debugger. So there is no extra connections that we need to do other than the TX pin from the microcontroller to the RX pin of the WCH link debugger. Let's head over to the MounRiver Studio. Here is our UART TX test example. Here I am using the UART printf initialization function. If we click on the control button, click on the function, and here is the definition of this function inside of the debug.c source file. It does initialize the pin D5, which is the TX pin of the UART number 1 on this microcontroller, and it also initializes the UART module at the specified baud rate. This function will enable us to use the printf, as you can see here, to send direct messages over the UART. I have also added and commented this UART1 initialization function in case you don't want to use the built-in function. It does pretty much the same thing. It initializes the pin used for TX, the pin D5, and it does initialize the UART number 1 in the TX mode. Initially and only once, before running the infinite loop, we will print the system core clock and the chip ID, which is unique per microcontroller. And in the infinite while loop, we will print this text message, which contains an integer number, which is this C counter that starts at 0, and it keeps incrementing until it overflows at 255 back to 0 and over again. We will build this code, flash it to the microcontroller using the download button, and it has now been flashed. I will open the serial terminal from the Arduino, which can be easy to use. Make sure you are selecting the correct COM port. Let's open the serial monitor, and as you can see, it's printing the serial messages. We can also use the built-in terminal inside of the MounRiver Studio. Click on Window, Show View, and go to Others. And here you need to select the terminal. It will open here. I will open a new terminal. Make sure that it's the correct COM port, which is COM3 for my case. I have selected the correct baud rate. Everything seems okay. I will click to open, and here you have it. You can disconnect, and it has been terminated. It's a success. We can maybe we can do another test. I will remove this text. I will keep only the number. I will reduce this delay, and I will build and upload this code. It's now going to print only the numeric value, which is the counter C going from 0 up to 255. I will open the serial plotter from Arduino. This glitch at the beginning, I believe, because of the messages that we have sent at the beginning, and it seems working okay. We will stop here. We will move to the next project example, which is ADC LED dimmer. We will use both of the ADC and the PWM output. We have seen the PWM part. We will not repeat this part again. We will just have an overview of the ADC. This is a typo. The ADC is only 10 bits in resolution, as we will see in the reference manual. As you can see, it has similar features to the STM32 ADC. However, we should not assume that it's going to act just like the STM32 ADC. Every channel can operate in single continuous, can trigger intermittent modes. These are sampling procedures that are supported by hardware. It can be right or left aligned, has a programmable sampling delay time for each channel separately, self-calibration, external triggering, etc. This is the block diagram of the ADC. It has injected channel group, which is like STM32. It has also some roles for group channels, external trigger pins, as you can see here, and I believe that's all. Yeah, I didn't look very deeply in this ADC. However, I believe you can benefit from my STM32 ADC tutorials, which explains the single channel, single conversion mode, single channel continuous conversion mode, multi-channel single conversion, multi-channel continuous conversion, external triggering, injected channels, etc. They will give you an overview for the operating modes for ADC. However, in this test example project, we will use the ADC in single channel, single conversion mode. We will use only one channel. We are not using the scan or sequencer or whatever, and we are doing only single channel triggered by software. The 10-bit result from the ADC channel conversion will be sent to the PWM to control the duty cycle of the PWM output. For the ADC input, I'm going to use an external potentiometer connected to the ADC channel number 2. Let's have a look on the microcontroller. The pin number C4 is the analog channel input number 2. This is A2 means it's an analog input channel number 2. A1, A0 are the ADC channels number 0 and 1. These pins are used by the external oscillator. If you are not using external oscillator, you will gain more ADC channels. This is ADC channel 6, 5, you get the idea. So we need to configure the ADC pin to operate in the analog mode. We will copy this code into our MounRiver Studio project. Let's close those, and this is our code for the ADC test example. We will initialize the PWM output from timer 1 channel 3, which we have seen previously, and next up we will initialize the ADC in single channel single conversion mode and enable the channel number 2. Here is the initialization function for the ADC. Enable the clock and configure the pin number C4 to operate in the analog input mode. This is the mode that we need to select, and these are the ADC configurations I'm using. I will enable the ADC and call the calibration function. You can remove this calibration part from your code. However, it gives a little bit more or better linearity for the ADC readings at the end of the day. So I will keep it as it is. Last but not least, the potentiometer ADC read function. This function triggers the ADC. It configures the regular channel number 2. Here is the potentiometer channel, and it selects the sampling time of 3 clock cycles, and it starts the conversion by software trigger. Wait for the ADC result and return the result of the ADC conversion at the end. This is polling technique. You can also use interrupt or DMA. I will mention more resources for firmware examples for this microcontroller. However, this is the test application we are going to use in this demo. We will call the potentiometer read ADC, and we will write the result into the duty cycle control register for the timer number 1, and we will insert a little bit of delay. We will build this project and flash it to the microcontroller, and as you can see, by adjusting the potentiometer, we are controlling the brightness of the LED on the PCB board, and you can also see the PWM signal on the scope by probing the pin number C3. And that's the last project we are going to test today. Before concluding this project, I would like to mention that you can easily add a reset button externally, just like what you see here on this breadboard. I have added my reset button to the pin number D7, which is the reset pin. This pin, pin D7, is the hardware reset pin, and the ground. That's all what you need to add an external reset option. For more firmware examples for this CH32 microcontroller, you can use this WCH link. We need to enable the English translation. These files has the datasheet, the reference manual, and some firmware examples to get you started with ADC, DMA, external interrupts, flash, op-amp, etc. I should also mention that there is a very helpful GitHub repo by Charles, who has also a very great YouTube channel. He has suggested this Git repo to me in the previous video comments, because their GitHub repo has an ADC assisted touch sensor library. I was curious to check it out, and it's a different technique from what I am using for the capacitive touch sensing, which depends on the CVD. We will discuss it later on, but I wanted to say that this GitHub repo has a lot of contributors and it has a lot of examples, and I believe it's very helpful if you intend to use this microcontroller in a lot of your projects. There is also one comment from the previous video about the capacitive touch example, if it supports adding acrylic sheets or glass. Here is a test using this 1.5 millimeter acrylic sheet, and I should say that yeah, it does work with acrylic sheet or glass, but it needs some adjustment in the parameters, as we will see in the future when we get to the CVD capacitive touch video. Until then, you may need to subscribe to get notifications for the upcoming videos. I hope this was helpful, and I will see you next time.